Hi, I'm Greg Kick. I work at Google on the Java Core Libraries team. We've brought you such things as Guava, some contributions to Juice, handful of other things here and there over the years, but sort of most notably Guava. In the past, I worked on data liberation, which people may or may not have heard of. Takeout. In a former life, I wrote JavaScript for that. And now I am working on dependency injection, and specifically not Juice, but Dagger, and now the redesign, Dagger 2. That's me. I want to do a quick couple questions about you guys. When I say dependency injection, raise your hand if you know what I'm talking about. Oh, good news. The first couple slides will be real quick. And then as we talk about dependency injection, there's been many frameworks over the years for getting that done. We have, for example, Spring. Any Spring users? All right, and some groans for Spring. Sorry, Spring. How about Juice? Okay, a few fewer. And then has anybody had the opportunity to pick up Dagger 1? Very few. Okay, so it's good to keep in mind as we move along. Because of the microphone situation, normally I would say interrupt me, but I think we're doing some recording, we've got some mics, there'll be time for Q&A at the end. All right, so let's get started. If the presentation works. Uh-oh. Hey, almost. There we go, perfect. So like I said, I just wanted to do a quick overview of sort of what dependency injection is. Everybody seems to have a pretty good idea, but let's just make sure we're all started on the same page. Dependency injection is a nice little design pattern for your Java classes. This is the Java user group. We're going to talk about Java the whole way through. And on the left over here, I have a simple fictitious coffee maker. If we were going to model a coffee maker in Java, and we're going to pretend like it has only a heater and a pump. And so in order to make coffee with my coffee maker, I need a heater, in this case an electric heater. I need a pump, in this case a thermosiphon. And because a thermosiphon requires heat, that's the thermo, we give it the heater as well. And so my coffee maker class has a method called makeCoffee. And if I were to write my application from a main method, I would make a new coffee maker, tell it to make coffee. That's without dependency injection. Everything that I need to make coffee in my coffee maker, I instantiate myself in the constructor. Dependency injection takes the dependencies of that class, the things that it needs to do its job, and has them passed in rather than created itself explicitly. And that's the highlighted portion over to the right. The constructor just takes two parameters, sets them, and relies on somebody else to give it its dependencies. Dependency injection. Go figure. The main method down there is the example of how that might be done. In order to make my coffee maker, I must first make my heater, must first make my pump, then pass it to the coffee maker to make coffee. Great, great. The reason we do this, or at least the claims that I'm going to make for the reasons that we do this, is you can do things like easily swap in fakes for testing. If I'm going to write a unit test for the coffee maker, I can make a fake heater rather than an actual electric heater, because electricity is expensive. We can also easily reconfigure these different types. If I, instead of an electric heater, want to use some crazy solar-powered heater, then I can go ahead and do that. I can also, kind of do development a little easier in parallel. Somebody else can work on the heater while I work on the coffee maker. If they change the constructor for the electric heater, that doesn't affect my code, which sounds great. And all of that wiring that happens in the main method, I want to be explicitly clear, we can do that wherever. People have come up with all sorts of ways to get that done. The part that we want to focus on is passing the parameters in rather than making them yourself. In pictures, this looks like this. I have my coffee maker, it includes the thermosiphon, it includes the electric heater. With dependency injection, take all those things apart, and via the interfaces, I declare my dependencies. Everything's nice and separate. So what's the problem? Well, for big applications, for big non-coffee related applications, taking all those dependencies, wiring them all together, there can be a ton of boilerplate. This is, ironically, part of the implementation of Dagger 2. because you can't use Dagger 2 and Dagger 2, go figure. So I have to do all of this stuff by hand. This is just one tiny little confusing snippet that I have to manage myself. It's a pain. The biggest portion of the pain is that all of those things have to be in the correct order. Dependency request factory has to come before provision binding factory because it requires a dependency request factory, yeah, blah, 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 all the way down. It's ugly, it's a nuisance. We don't want to have to do that by hand. And some people say, yeah, that's true, but I can manage it myself. No, really, I'm a great software engineer. I've got this. As examples, we had an Android application that had about 3,000 lines of that because I looked, it was 3,000 lines. I checked before I wrote the presentation. 3,000 lines of exactly this. For a large server-side app, it actually flushes out to be about 100,000 lines of exactly this code. It's depressing, it's monotonous. We're going to try our best to not have to do that by hand. The question is, how do we get the benefits without the boilerplate? Well, we started back in 2002 with Spring 1 and 2. This is why I asked about Spring. We loved Spring. Back at that, it was revolutionary. It popularized dependency injection, or inversion of control, or the Hollywood principle, or what you want to call it. You had a way to declare all of your dependencies, and it figured out that really monotonous ordering for you. No matter how you shifted your dependencies around, it would always instantiate the things in the right order. Everybody was really happy with that. The best part was that all of the objects that you were doing, you were manipulating with your dependency injection framework stayed exactly the same. Well, that sounds like magic. How did it stay exactly the same? It was XML. I'm sorry. It looked like that. No, it was cutting edge at the time. Let's not make fun. You would define a beans.xml file, and you'd have little snippets of XML here and there. But the things to note, the good things, the things that we still do today, it's declarative. There's no logic here, there's no for loops, there's no anything like that. You say that I need to make a coffee maker, it takes a heater. Refer to the heater that I've defined below. That heater, it's an electric heater. That's the class we want to use. It also takes a pump, so on and so forth. And the point to note specifically is that those things do not have to appear in order, right? That's the problem we're trying to solve. We don't want to have to constantly reshuffle everything when we swap a dependency. We don't want to have to manually figure out the ordering of a directed acyclic graph, for those of you that love graph theory. And it ends up looking like this. It's the exact same DI picture, but now we've applied some XML to it. Where we used to have a coffee maker class, we've got this little snippet that represents the coffee maker. We have those constructor arg references. That's what gives you your dependencies between all of those things. And the bean factory is the Spring class that sort of wraps that all up and does the work for you. Great. So, like I said, solved the ordering problem. It also solved instance management and scoping. Feel free if you're curious to talk, or if you want to ask about scoping later. It's kind of a complicated topic. We can Q&A it later, but for the most part, we'll just take it on faith that it does that. But there were issues, possibly more issues than solutions, as my completely jaded bullet points might lead you to believe. XML's not so good. We don't like XML. And all of the validation of that configuration file happened at runtime. If you made a typo anywhere in one of the names of one of your bean definitions or bean references, you were going to start up your server before you found out about it. Same thing with validating the graph itself. Even if your configuration file was great, at runtime we have to figure out to make sure that all the dependencies were satisfied. If you forgot a constructor parameter, you can't make an object. It also had some issues with tracing the application flow, trying to swap back and forth from Java to XML, and it was a mess. And a map-like API that we will talk about in just a little bit. So that was Spring. Juice came around somewhere around 2006 with, I looked at the very first CL for Juice. It was adorable. But it, all the way back to sort of the mid 2000s. And Java 1.5 had just been, released, sort of up and coming somewhere around there. And Juice said, I can use all of these new language features like annotations and generics to start doing the things that I used to have to do in XML. Now I can do in Java, with the annotations that I have available. And what that did was it decreased the configuration and decentralized the configuration. No more giant XML files, and the annotations that define your configuration were close to the code. Great. And entirely written and executed in Java. Quick informal poll, how many people have installed the Spring Eclipse plugin that tells you how the XML relates to the Java? Yeah, there's like 3 people, because getting it installed was sort of a pain. I don't blame you. So now we want to talk about, where did all that XML go? How do you do this in Juice? Who can spot it? Who can spot the one little bit of configuration? That looks remarkably like the coffee maker I started with, except that guy. It's barely any configuration at all, but just applying one annotation to that constructor says, I now participate in dependency injection. A little better than angle brackets. We also have these things that say how the objects relate to each other, how abstract classes relate to concrete classes. And for that, we have a little bit more work to do. The top is an example of how you might do it with the, sort of the Java API using class literals, and the bottom defines how you might do it with a method. So in the top example, I want to say that my heaters are all going to be electric heaters. In the bottom, I say that I want pumps, and I'm going to use thermosiphons for my pumps. And that's the again 100% in Java, but expressing all of the same concepts that we saw in XML, but now, in just pure Java code. Back to our friendly graphic. We're kind of showing how that all ends up working out, is that the same coffee maker was now defined by that @inject constructor. So much easier than XML. We have that provides method that defined the pump. We can take it on faith that there were @inject constructors for the thermosiphon. Juice actually has a nifty little feature where if you don't have an @inject constructor, it will just assume default constructors work, so the electric heater gets to participate, and we have that binding. The exact same concepts, just in a little bit different configuration language. And rather than a bean factory, we wrap it all up in an injector. The one last thing I want to point out is that in the Spring XML version, in order to define the heater, we had to define 2 references. We had to say that the coffee maker depended on a heater and the thermosiphon depended on a heater. Now we have 1 definition for the heater. We are making huge strides towards collapsing our configuration language. If, for example, you had a database that you needed to access from 10 different places in your application, you get to bind it once instead of having a line of XML for each of the 10 places you might need to use it. That said, you might also want to note that there are 2 ways that we bind abstract types to concrete types, or in this case, interfaces to concrete types. We don't generally prefer 2 ways to do things, and that tended to get a little confusing. But this all sounds great. What's the problem? Why is Juice not our silver bullet? We still have a lot of issues at runtime. Juice users, how many people have seen stack traces exactly like this? How many people found them immediately helpful? For those of you in video land, it was 0. Yeah, the problem is, and it's the same problem that Spring had, you have to start up your application or start up some integration test or something of the like, and you get this stack trace that all it's trying to express is you forgot a binding. You forgot, in this case, a binding for the pump. What happens if you declare a binding twice? An equally sort of convoluted runtime stack trace that has a lot more noise than we would probably prefer. And this has been long, basically since day one, a source of frustration for Juice users. Another question might be, how do we debug a Juice application? We're creating all these objects. What happens if we turn on the debugger? The top example is what happened when we did it manually. We had 2 stack frames. One was the main method, the other one was the coffee maker. In Juice land, the exact same breakpoint becomes that. It's a little frustrating. There's a little more to trace through. There's a big sort of runtime process that you have to deal with. Or worse yet, if you enable the wrong feature, you will just get breakpoints that your debugger doesn't know how to deal with. You can't possibly run a debugger against some of these applications. And you get some curious things in the middle of those stack traces. Coffee maker $$, enhancer by juice $$, some hash code $$, fast class by juice $$, more garbage. That's not particularly helpful in most cases. And if you try to go figure out what that thing is, it's going to tell you source not found over and over and over and over again. Not the friendliest experience. But worst of all, and this is the same problem that Spring had, the code becomes untraceable. How do you know which implementation of heater is going to use? Now you have to go track down a binding. Tracking down a binding sort of feels like getting a big pile of Legos, somebody saying, okay, there's a house, you figure out how it was put together. It's a little daunting sometimes. And if you try to do things like, well, okay, Eclipse has a feature where I say find all the places that somebody's calling my constructor. In your juice-centric application, there will be exactly 0 places that somebody's calling it the constructor, because it's all done by reflection. So your normal tools that you might use to traverse your code, not so helpful anymore. And finally, the configuration, the configuration we laid out in Java. It's dynamic and it can be conditional. In this case, this is a snippet out of one of those configuration modules. And somebody did something, very earnest. They said, okay, my application, under some conditions, I want a certain type of authentication. Under other conditions, I want a different type of authentication. So in the middle of my module, I checked to see what a flag did, picked one or the other. That seems like a perfectly reasonable thing to do. But back to the Lego analogy, if you imagine that big pile of Legos, and every time you tried to put that house together, the instructions kept changing, how easy might that be to figure out how the pieces might fit? It can be frustrating, to say the least. So given all that, we've heard some good and some bad with Juice. We've got binding discovery. I can just find those things that are annotated with @inject. They get to participate without a lot of extra configuration. So we greatly reduce the configuration, no duplication, things like that. And that configuration all lives right next to the Java code. We don't have to go to a separate XML file to find it. We can just be right there, go take a look. And it's all in pure Java. All of these things sound great, and for that reason, Juice has become, can't think of an exception. Juice is almost certainly the most popular framework that we have in Google applications for Java. It's used virtually everywhere. I mean, hundreds and thousands of classes are being managed with Juice. But it had issues. The runtime validation of the graph, still a problem. Untraceable application flow, pile of Legos, still a problem. Synthetic classes that you can't inspect and have to go look at the Juice source code to even guess at what they might be doing, still a problem. And that map-like API. So Dagger 1 came along. Dagger 1 actually is not, so whereas Juice was a Google effort, Dagger 1 was former Googlers working at Square. They decided to take their crack at the problem. And they basically said that the configuration API, basically all of the solutions in that that solution column, all that stuff was great. So we just take all of the bits of that Juice API that you can inspect statically. That was the caveat. Everything that the compiler knows ahead of time and you don't have to execute in order to figure out the behavior, that's the part that we want. We want this thing to be, you can just, your compiler will know what's going on. You don't actually have to start up a server to figure it out. That's the API. And then for the feature set, we're going to toss out everything that may be a little dangerous. Juice was used to great effect, but if people are really frequently shooting themselves in the foot with a feature, let's toss it. And then the combination of those two things, let them go through each of the dependency injection features that you might want and stop doing the things at runtime and start doing them at compile time with annotation processors. And this is a bit of the magic, is that error reporting now happens at compile time in Dagger 1. We'll get to some examples of that. But the other bit is you can just do things more efficiently. If you don't have to do reflection. No reflection is always cheaper than reflection if you're doing the exact same thing, so let's do no reflection. And we take all of that overhead out of asking for a new instance. the graph looks almost identical to what we saw in Juice. The difference is that where we have we used to have that API where you could bind things with class literals. Now everything's a provider method. It's a little more verbose, possibly, but that's the part that we can know statically. The compiler can look at that and figure out how your application is wired together because it's got a return type and it's got parameters. The other difference, which we don't quite show here, is that whereas in Juice, abstract module was a class you had to inherit, module is now an annotation. Really not that interesting a difference. But what happens when we forget bindings? I claimed that we got errors at compile time, and we do in fact do that. That little red squiggly is Eclipse dutifully reporting that there is no binding for pump. It was required by the coffee maker via the drip coffee module. And Java-C will tell you, Eclipse will tell you, whatever your IDE will tell you. That happens immediately as you type in Eclipse because of its constant compilation. We no longer have to start servers to figure out that we have missing bindings. The development lifecycle becomes very, very quick. What happens if you declare a binding twice? The exact same thing. You get a red squiggly line on each of the duplicates. It tells you exactly what they are, and it tells you, as immediately as compile time can make it. What about debugging? Better. I will argue that it's better, but it's not quite perfect yet. The thing you will notice is that we still have weird classes with $$ in them, but at least we tried to give them friendlier names. We call them inject adapter. It adapts your class to injection. Go figure. So we give them names meant for humans to read. But the most important bit is those inject adapters have source. You can look at it all the time, without exception. You can always go look at exactly what it is doing. So you have a clear path of code from your main method all the way down to the coffee method or coffee maker constructor. So I claim that you can look at the code. Let's do that. Uh-oh. That's a lot of not so friendly looking code. It does generate code. You can trace through it. Maybe a lot of times you probably don't want to. There's a lot of stuff going on. There's strings that look like class literals. There's actual class literals. There's asking for class loaders. It's certainly a far ways from perfect. But we do all sort of boil down to kind of the holy grail of this is what we were trying to do in the first place. We've just got a lot of extra cruft that we might want to get around or sort of toss out. So what did Dagger 1 do for us? Well, we get compile time validation of big portions of the graph. We saw that you get errors pretty quickly. Easy debugging. We can have an entirely concrete call stack. And highly efficient provision. I think I probably should make that a little clearer. Did you notice that in creating my new coffee maker instance, there is no reflection? Reflection is not used to instantiate a coffee maker in any way, shape, or form. Reflection is used to figure out how everything fits together. So if you have applications with sensitive startup times or you're creating graphs per request, that's going to be an issue for you. But if you already have a graph and you're just asking for instances, it's going to be nice and cheap. The issues are that I think it's pretty, I don't know, I feel a little bad calling it ugly. I had a hand in some of it, but it's a little ugly. And it's also runtime graph composition. The reflective part where you wire everything together, that's still runtime. So there are still like classes of errors that you can see at runtime, which is not ideal. And reflection makes inefficient graph creation sometimes. And if you want to trace through your application for creating an instance, great, everything's good to go. If you want to trace through your application for how to compose your graph, that's where we're still a little lacking. And that map-like API that we just can't seem to kick, still there. So we got together one day, said, all right, how do we finally take a shot at fixing these problems once and for all? Or, better yet, what are the problems? And I continue to argue that dependency injection has worked since roughly 2002. And certainly as of Juice in 2006, when you do things right, everything's easy. The parts we need to focus on are what happens when things go wrong, and particularly traceability. I want to be able to navigate through the entire application, all parts of it, creating the graph, getting a new instance, with Eclipse's find usage or open declaration. Those nice little hotkeys that we all know and love, they should never not work. And I also want to trace through code that looks kind of like what I wanted to write. If I were to undertake doing 100,000 lines by hand, I want the code that's generated to look exactly, or within reason, exactly like what I would have written myself. We also want to clarify the API a little bit. Simpler module declarations, they can get kind of convoluted sometimes because of how things are composed at runtime. And no more maps. That map-like API, we're getting rid of it once and for all. And then performance. Performance was actually one of the big motivators for for why we want Dagger 2. The Android, your mobile device, had pretty good success with Dagger 1 because you start up your application once for the most part, and then you ask for new activities, you ask for new things, and that reflection cost that they were paying pretty infrequently. If you wanted to use Dagger on the server side, and we have been using Dagger on the server side in one of our larger search applications, one of our larger search services, the per request overhead of creating big object graphs was really starting to weigh pretty heavily on Dagger 1. And we'll talk about some of the results for having moved on to Dagger 2. The other thing is we don't want to code around the framework. Every time you find yourself caching something because it's slow, that's a burden we're placing on our users that we don't want to, and we want to make sure that no one ever has to do that with Dagger 2. So what do we do? How do we do it? More or less, we like the API for configuration. We liked it in Juice. We continue to like it in Dagger. It works. Stick with the configuration API. Those are provides methods and @inject constructors, all those things that JSR 330 defined for us. We're happy. The compile time code, we want to generate nice, simple code for the entire stack. No more reflection. We're getting rid of reflection entirely. That was a bit of a tricky goal. We'll see how we did it. We also want to validate all framework and configuration preconditions at compile time. If we don't have reflection and we don't have a runtime presence, we obviously need to check all the errors at compile time. Otherwise, your application would just fall over and not compile. And then we finally wanted to unify user-defined types with generated types, but we wanted to do it in a way that was limited, clear, sort of intuitive, something that you don't really have to figure out. And that's a lot of times the challenge with user-generated code. And for that, we drew inspiration from a framework, framework project, whatever you want to call it, called AutoValue. If you are sick of writing equals hashcode and toString, I highly recommend you go look into AutoValue. Different project, also code generation. That's where our inspiration came from. Go take a look. But what AutoValue did, and the sort of the mantra they set forth was, step one is constrain the problem. Make the problem solvable using code generation, and then generate the only reasonable implementation that anyone would ever expect. Seems straightforward. So that was our strategy. Here's how we did it. We started with JSR 330. That's the thing that defines @inject, a couple scoping annotations, all those DI things that you're probably familiar with, having used the DI frameworks. The funny thing is it only actually defines one non-annotation type, and it's called provider. Provider is an interface, and it just says, get me an instance of whatever I'm a provider of, which seems pretty straightforward. In our coffee maker case, I'm sorry, I knew it would happen. There's a typo. That should say provider of coffee maker, not provider of tea. But imagine that said provider of coffee maker. By the time anyone on YouTube sees these slides, it will say provider of coffee maker. So for provider of coffee maker, you just say, hey, I want an instance, call get, you get a coffee maker. That seems pretty straightforward. The trick is figuring out how we need to implement, what we generate that implements provider that will work for our DI framework. Here's what we make. For a coffee maker provider, we call it coffee maker $$ $factory. quick note about the $ is anything that we don't expect users to explicitly have to deal with, we put double $ in it. If you find yourself, typing in your IDE and you type $2, you're doing the wrong thing. But because they have to be public classes for a variety of reasons, we, couldn't just hide them so people couldn't touch them. We just had to make them ugly. So coffee maker $$factory basically does exactly what we wanted to do in that original main method, but instead of asking for new instances, it just asked for the provider of a heater and the provider of the pump. It knows exactly one link in the graph. It says, in order to make a coffee maker, I need a heater, I need a pump I need a heater, I need a pump. So get the provider for those things, call get, return a new coffee maker. And that's all happening right down there. With the layer of provider indirection, it's otherwise exactly the same. And we generate that for you. And I would argue that most people can, if they're familiar with providers, not having seen this for the first time, it looks pretty straightforward. It's certainly a lot shorter than our previous version. The other thing is we all have provides methods, which is a method that provides a value. We saw those in the previous examples. The only difference between a factory for a constructor and a factory for a provides method is that you just get an instance of the module and invoke the method. That's happening down there. In order to provide a pump, I need a thermosiphon, because that's my implementation of pump. I generate code that just calls the method and passes in the thermosiphon. Pretty straightforward there too, I think. Now we get to talk about that map-like API. This is the client API. This is how you actually ask for a coffee maker. In Spring, it was pre-generic, so it was, make a bean factory, pass in a string, cast. In Juice, we had Java 1.5, so we got to be a little more clever. We got to say create an injector by passing in a my configuration, and then get an instance of a coffee maker, and it automatically does the right things with generics. But we're still passing in class literals, so obviously we're still in reflection land. In Dagger 1, like I said, that was exactly the same. It was still reflection. It still, looked more or less like a map of class to object. In Dagger 2, this is the crux of it. This is the part that changes. This is the part that we are, doing most differently. We say here is a coffee maker component, and component is the word for, the interface that Dagger 2 needs to implement that just gives you instances of all the types you define. So as a user, I say, I want a coffee maker. I define an interface that says, give me a coffee maker. Just a method, no arguments, returns a coffee maker. And I toss the @component annotation on it. I list out all of the modules that I need to make my component, and if any of them are missing, we get the compile time errors that we expect. And what it does is it generates a class with the same name as the component, but prefixed with Dagger _ that knows how to take all of those bindings together and create your coffee maker. So we just say Dagger _ coffee maker component .create, and we get an implementation of that interface. We never have to hold on to that concrete type again, but that thing knows how to make coffee makers for me, and I just call the method with the method name that I gave it. Sounds like magic. Here's the magic. We literally write all of that horrible boilerplate that we used to have to write by hand exactly as you would have to write it if you wrote it by hand in the generated implementation. It is all of the same logic in all of the same order, just written out for you. I am going to admit to this being slightly different than what you would actually get out of the tool, because I had to kind of keep it a little more compact to live on a slide. With very few modifications, this is exactly what you get. It just goes through, says, here are all the things that don't have dependencies. I can make them first, and then all the things that I need, wires them all up, stores the references to the provider, and the coffee maker method, the get coffee maker method that I defined on my interface, the implementation is invoke that provider, which in turn invokes all the other providers, which in turn invokes all of the other providers, all the way down. And as far as we can tell, it is the single most runtime efficient version of dependency injection that you can possibly have. We have yet to dream up anything better. And there are a couple layers of indirection in here, a couple extra provider objects, and for the most part, Hotspot seems to do its job and make all of those things as cheap with all the inlining that we could hope for. So what have we done? We have compile time validation of the entire graph because we're generating the entire graph. We have super easy debugging because you can literally just trace through line by line and watch it invoke all of these providers. Fully traceable. You can see all the fine usages. Let's go back to that slide. Every one of those factories that we generated in the first step, we have references right there. We can just, F3 in Eclipse, open declaration. And the API is finally, once and for all, a Java object just like everything else. I say I have this interface, here are the things that I need, that's what I work with instead of map type things with class literals. And most importantly, performance. I guess this is the part where I get to tell you exactly how performant. So we had a pretty large search service that's serving a lot of traffic. And the more Dagger 1 we adopted, people were very happy with the compile time errors, but people, our SREs, the people in charge of monitoring just how efficiently things are running, how many CPUs things are taking, they started to come knocking on my door saying this is getting worse and worse and worse, and we have to stall some of the migrations to Dagger 1 because we're burning too much CPU. So I kept saying, hold on, we'll get Dagger 2. It'll solve all of our problems. It is theoretically the best we can do, so obviously that'll work in practice, right? It was earlier this week that I finally got to wipe the sweat off my brow to the tune of about 13% of per request CPU at Google scale. That's a lot of CPU. We made every single request all of a sudden 13% cheaper by moving just dependency injection. That was a very big win. In Android world, that could be 13% of your application startup time, depending on how your applications are wired. But I think most importantly, I continue to argue that you just can't do any better. But I'm not going to lie, there are some issues. There are some things we traded in order to get all of these great benefits. It's less flexible. Reflection is nice and magic because you can do virtually anything you want. You can inspect your entire application, permute it in crazy ways, generate bytecode. We don't let you do any of that, so you can't do any of that. We think that's an okay concession. There's no dynamism, no more flags, no more recomposing your application at runtime. You still have all the same conditionals, below provider methods and above your components, but we don't let you, sort of retool how the framework is behaving dynamically. That seemed also kind of to be an okay concession because it was causing a lot of people a lot of confusion. And the biggest issue that we are finding is that because of these constraints, there is no automated migration path from Juice. You can't say, oh, swap out these set of imports for this other set of imports, and all of a sudden your application becomes a lot faster. And as I mentioned, we have a lot of Juice code. So if you want the benefits of Dagger 2, you're probably going to have to do a little bit of work to migrate your app from one to the other. And again, that's it's a concession, but I think that it's probably fine, specifically as we, sort of software engineering community at large seem to spawn new apps faster than we know what to do with. So if we only target new apps, I think that's probably not half bad either. So what's the status? Where are we? Can we put this in your hands? This very specifically, you guys might have noticed, wasn't a tutorial. I didn't show you how to do it. I showed you why we do it, because how to do it isn't quite there yet. We are, roughly speaking, feature complete. If everything goes well, it runs. And like I said, we've seen this running on something very like production traffic. But we have bugs. We have bugs that we have to squash. We have error messages that we need to make a lot better. In fact, my partner in crime over there and I spent, probably a good hour and a half locked in a very hot room debating over, just what we're going to show you when you have a cycle in your dependencies. We are working very hard and taking that very seriously because we don't want to give you something where your first experience with it is, I made a mistake and the thing blew up. We have some preliminary performance tests that I mentioned, and we are developing a migration guide, not from Juice, but from Dagger 1. We do fully expect to support. I have Dagger 1, now I want Dagger 2. They're similar enough that I think we should be able to give you a pretty clear path forward. So that's where we're at, and we expect certainly I will promise that we will have this, in your hands, in the open source project's hands, within, certainly within the quarter, in some form. But you can go check out the code, build it yourself, poke around. But when things break, it's sort of at your own risk right now. Resources for all of this. We've got the Dagger 1 page, the Dagger 2 design doc, the Dagger 2 code. We have some spin-off projects that are probably worth taking a look at if this is the sort of thing that interests you. Compile testing was a big effort where we made some tools for testing annotation processors. If you ever write one, I highly recommend looking at that. And AutoCommon is some common libraries for annotation processors.